I think the attendance is low right now, so we will wait for 2 more minutes. Okay.
Excuse me, I had put a question in chat. Would you mind taking a quick look for me, please?
I didn't see it, so have you typed it in the chat?
I did, but before you joined, because I had to resubmit the assignment with the images, it says that it is late. We're not going to receive
Oh, I
lesser.
see. So this is what's happening. So we will not count late submission if you re-upload the image. Okay, so we will not deduct mark for that. Is okay?
Just sure.
You're welcome. So there are some images that are not up to quality. Okay, so because finally these data will be used for the final project. So if some of you like the contact by the TA, try to fix that. Okay, if not, we will probably have to deduct mark accordingly. Okay, I discussed with TA and find some of the annotations are not, for example, not tight or not correct or missed a lot. Okay, but yeah, so if you are contacted by the TA, just try your best to fix those. Okay. So I think I should not put it here. Okay.
Hey, just to clarify that, Dr. Yan, you were saying that the TA would contact us if those types of corrections were necessary, correct?
Correct. Yeah, if the TA tell you, hey, this is not okay, right? So we will give you a second chance to fix. Okay. Yeah, we will not just do that. Yeah. Mm-hmm. Okay, so I hope I answered the question. Let me see. Yeah, because the ultimate goal is to compile a data set that we can work with on the final project, which the purpose is not really to detect mark, right? So if we do that mark, but the data is of low quality, then the final project won't go on smoothly. Okay.
Yes, the idea of it was kind of cool. We're kind of like, it's kind of like a neural network, but weird the nodes, as it were.
Mm-hmm. Yeah, so we'll do image segmentation. These are the training data. Okay, I think the attendance is closing to 50, so we probably will begin after we reach 50. Okay. Let me see. I think I just released today's slide. Okay, previously we talked about SVD, and then because of the last week, so we have the wellness day, so we watched the video together, and so we have some gaps. So today we will recap what is SVD, and then we will discuss a bunch of SVD applications. Okay, before doing that, because some of the problems there, actually we need to use some multivariate optimization stuff. So we will cover also some preliminaries. And if you have taken my machine learning course, this is actually a basic slides here. So, but we will also cover it here, just in case some students have never heard of these things. Okay. Yeah, we reached 50, so probably we should begin. So firstly, there's a preliminary slide. If you open the preliminary slide, you will see something like this. And so let's briefly go through these preliminary chapters first, okay? Let me call out my pen in the meanwhile. So, I think I should first switch to mine. Okay. So, when we talk about like optimization, basically what we have is we are considering a function y, for example, equal to fx. Okay. Let me take my pen maybe. Yeah. So this will be a function, right? But what we want to do is that we want to, for example, optimization, we want to find a particular x that, for example, minimize y. Okay, we have so many different x, depending on this function. Okay, whatever function we want, right? So this is an optimization problem, And additionally, we may kind of have some additional constraint, like x cannot be this, cannot be that. Okay, so this is basically the concept of optimization. And in reality, usually we are talking about not just the x and y that are scalar, right? So it's just one value. That's fine. Right? That's a regular case. Right? So we use a so-called gradient descent to do this method. For example, if you can, for example, you have a y function, which is a function of x, right? What you can do is you can go, you can compute the derivative, which is the fastest direction that increases your value, okay? But what you can do is you can do on the opposite side, right? So you can do gradient descent, opposite side. And then when you are here, you can compute another derivative. Maybe this time it will be a little bit less steep, and so the value is smaller, and all the way here. Here the value will be 0. Hopefully you will reach the smallest value here for y. Okay, that x is what you want. So this is the idea of why we want to take derivative. So we will take a negative derivative direction with some step length, or we call it learning rate. Let's say alpha or epsilon. Okay, but this calculus, right? So this is a regular calculus. Right? So we see maybe in calculus class, right? Log x, if you take a derivative x is 1 by x. Right? So if you remember those kind of concepts. Okay, and so we can generalize this actually to high dimensional case. Okay, for example, this x doesn't have to be a scalar, right? It can be a vector. For example, f equal to f x vector. Okay, it could be equal to like let's say the vector has 3 items. It can be x1, x2, x3, okay, something like this. Right. Then we want to find 3 values of these that minimize y. Okay, right. So then this becomes this kind of case, right? This is a vector. Okay, and this can even go to matrix. Right. So the input can be a matrix. Right. It's not just a 1 row or 1 column. Right? It's 2-dimensional. Right. Similarly, you can also have something like so y, right? So maybe y1 is f1, y2 is f2. Okay, so then you can have a vector one. You can even have a matrix one. Okay, so there are different combinations that you can do. Right? Okay, so you want to find that matrix that let's say minimizes y. Okay, if it's a function over the matrix. Okay, so these are the concepts we are looking at here. This is called a multivariable calculus because it's not just a one variable. Okay, it's a lot of values. Any questions? If not, we will continue to look at this. This we will just use the canvas, browser to do it. Okay, so because there's not much animation. So first, let's consider the particular case. Actually, it's corresponding to a particular case up there. Okay, up here. That we consider. We call it a vector calculus. Right? So the reason we call it vector calculus is really because you look at here. The x here, this is the vector, okay? This is the vector. And the y is a value, okay? You take a value, partial derivative to the vector, okay? Take a derivative to the vector. So here's an example. Here's how we can derive the gradient for the input. Right, so for example, this is our function, y equal to gw, but w is a column vector, okay? This is a transpose, so it's a column. Okay, so if we have this thing, right, how can we calculate gradient? How is the gradient defined? Right? So because w is a column vector, if we do gradient descent, we want to change w. Right? So the gradients should also be of the same shape, which is the column, okay, of n values. Okay. So this is just by definition. Okay, this is strictly this definition. There's no derivation. Okay. So if you think about the derivative of g over w, we can write it as the gradient, right? Or we can specify this is taking gradient over w, right? So the result will be, take this function to each item, okay? The first item will be the first element in the result gradient, okay? The last g to the power of the last variable will be the value for the last element in the gradient, okay? So this is just following the definition. I think this may be not necessary. Right, so so this is the first derivative, right? So what if we have the second derivative? Okay, so second derivative is called Haitian Matrix. Right? So because now if you have this n variables, okay, n input variables, your y is t. Okay, now if you take a derivative, right? So twice. Okay, if you think about individual value, you can first take a derivative 1 and then to 2 or to n. Right? So this actually. The Haitian matrix is saying it's a matrix. It's really, you first take a derivative I, and then take a wj, okay? Right. For the i's row and the base column element. It's really take a derivative first to I and then to j in this end. Okay, so this is the Haitian matrix. So like the second derivative. All these are definitions, okay? And if we define things like this, right? So maybe this one is not obvious, but this one is pretty obvious. If you do gradient descent, right? If you want to change W by this small delta to make the value smaller, the G smaller, of course their shape should be the same, okay? And they actually satisfy those very nice rules for the scalar case. So for example, if you look at this formula, we can prove this, but this is applied math, right? In some sense, right? So we are not taking math course. We will not discuss that. Okay. Because if you take a derivative f and g, right? F and g, it's equal to f take a derivative times g plus f times g derivative. Okay. So this is equivalent to what you see if w is scalar. Okay. Similarly, this is called the chain rule, right? So if you take a f to some value which is y and then y to w, right? So y is gw. Then first take f prime, right? So take a derivative, considering this is y. Okay. Then you need to consider, because y is another function of w, right? So you take a derivative y then to w. Okay. This is called the chain rule. So all of these rules are still holding when we generalize calculus into vector. Okay. So here, let's take a look at an example. Right? So assume that we have this function, okay? This function. Right? So A is constant, okay, by the way. Right? W is a variable, okay? So we have n, W1 to Wn, right? And we each one have a coefficient A1 to An. Okay? You can see that this is actually inner product. Right? So it's A is a column vector, A transpose a row vector. Okay? So this is like A1 to An, okay? Then times inner product with the column vector W1 to Wn, okay? So this will give you this. Okay? So this is basically this is the column vector transpose, which is A transpose. This is W. Right? I hope you can see this. Now, according to our definition, if you go back to our definition of what is this? Right? If you go back to our previous definition, we have here. So basically, we want to take G over each variable. Okay? So now let's take a look at it. So you want to take a derivative of this thing to W. Right? So it's basically first take a G first to W1. Okay. But this thing, you see, this is a summation. A summation, other item doesn't matter to you. Okay? Because they are taking derivative W1, only A1 W1 matters to you. Okay. And if you take a derivative W1, you get A1. That's a coefficient. Okay. And then you do the same for A2, A3, all the way to AN. Right? So what's nice about this is that you can use a more succinct notation here. Right? So what is this anyway? This is A, okay, this is A vector you showed before, as a row vector. Okay. So when we have this vector, right? So then we can say, hey, now if you take a G which is A transpose W, okay? Take a derivative W, right? Okay, which is here. Okay, what's the result? The result is A itself. Okay, this is A itself. Okay, so that's pretty nice property. Okay, so this is called the linear functions derivative. Okay, so this is equivalent to if you look at AX, right? If you have AX, right, X is scalar, you take a derivative X is A. Okay, okay, you A. Now we say if they are vectors, right? So then you are doing inner product. Okay, A transpose X, take derivative X, give you A. The transpose is gone. Okay, so that's the concept, how you remember this. Is this okay with everyone? If you have a question, feel free to ask. Okay. Now let's take a look at this function. So this function looks pretty complicated, right? So this is the generalization of y equal to ax squared. Okay. So this is just nothing more than just a high dimensional vector form of this. Okay. So now this x becomes a vector w1, w2 all the way to wn. Okay. And this a is a coefficient of the quadratic. This is a quadratic. So you can show easily, but we will not show that. Okay, I will just let you remember this. Okay, so probably you already heard of this, right? So it's called a quadratic form. Quadratic form, okay, in linear algebra. Okay, so this quadratic form is exactly the same this. So if you have some shape like this, which means you have a x1, the row vector xn, and then you have a matrix. Okay, let me see why. You have a matrix. Okay, it's a11, a1n, all the way to AMN. Okay, and then you sorry, I think this is really. Then you have a column vector. Okay, this column vector is exactly like before. Okay, exactly. It's just the same thing, but this is a row vector, so that's why you transpose. Okay, this is a column vector. Okay? Then you have a coefficient in the middle. Okay. If you time this out, you will find it's actually something like this. Right? So for simply, how to see this? Right? So what you do is for each element here, this is the coefficient. Okay, and then this is in ith row, so you take the ith element here, okay, which is maybe wi. Here we are right? And jth column, okay, and you attach the jth wj. Right? So then you can expand. Okay. This is actually a generalized version of the inner product. Right? If you think of this identity matrix in the middle, this is really just an inner product of this matrix. Okay, is a value. So this is actually a value you can see. Right? So because this is 1 by n, n by n, n by 1. The result is 1 by n. I hope this is okay with you. But if you expand this kind of a row, square, column shape, it's always going to be a value. Right? And if these two are actually the same thing, just this is transpose. Right? And then you can write it out like this. Okay? This is just like you need to memorize something like the quadratic form. Right? It's just like we asked you to remember SVD. Okay? If you derive it yourself, it's fine, but then you will find it's still this. You need to memorize. Okay. Any questions so far about the quadratic form? This form. I hope it is okay. So now that if you have this quadratic form, right, so again we are saying this is constant. Okay? This is like a. This is your x, x squared. Okay, this is your y. Okay. So in our usual case, right? So if you take derivative from of y to x, right? So what you have is 2ax. Okay, x squared becomes 2x. Right? So you have 2ax. Right? So let's directly look at the generalized solution here. Okay, is there any relationship? The answer is yes, because 2ax is what? Ax plus ax. Okay? And here we are all talking about scalars. Right? So if scalar transpose itself, it's the same. Okay? So A and A transpose the same. So basically, you can see they are kind of have some relation. Okay? So this is really the generalization of this quadratic. Okay, when x becomes back. Right. So now let's take a look at how we can derive this thing. Right. So we are saying, hey, this thing is your function, which is the GW. Okay. Now we take a partial derivative GW to W. Right. And how we get this. Okay. So now, firstly, actually, you can look at this function. Right. We know that the first element is what? The first element in the partial G, which is basically this thing. Okay. Take W1. Okay. So this is what we want to compute, and we will show this. So how to see that? So firstly, you think about it, right? So W1 can be either, this one can be either I or Bj, right? First, let's consider the case where I equal to 1. Okay? I equal to 1. In that case, when I equal to 1, any j, right? Any j is fine. Okay, all the summation over j is fine because this I is equal to W1, okay, is what we want to take derivative, right? And this is summation. So our coefficient becomes Aij Wj. Okay, again, I is equal to 1. So that's A1j Wj summation. Okay, so this is one side of it. And the other side is derived when we consider this other case. So we say j equal to 1. Okay? If j equal to 1, then if we do, so basically we are saying, hey, not this term, we only have one term we care about. That's because the other Wj is around to the W. Okay? So only one term, which is j equal to 1. And in that case, we are taking derivative to this one, this value. Okay, and the coefficient becomes this term. Right? And of course, because j is 1, so that's why we get AI1 and W. Okay, so this is just following the definition. Is this okay? Any questions here? So some of you may ask, hey, there's a special case one. Both of them are 1. A11 squared. Right? So A11 W1 squared. Okay. But this is fine, right? So because after you take a derivative, it becomes 2A11 W. It's A11 W1, A11 W. Okay. One goes to this term, one goes to this term. Okay, because this can be. So you can see this actually generalizes to the other values. Okay, so basically this one, right? You see this one. If you next time you take a derivative W2, right, the second element, okay, then this value becomes 2, and this generalizes to n, okay, because the last element is take partial derivative. Okay, so this all the way here is very straightforward, right? So how can we see this thing is this thing? Right? So that's the tricky part. Yeah, so the answer is, this is a linear equation. Okay, if you look at this thing, right? This thing, hey, I have a W1, Wn, okay? Then I have an A matrix here, okay? A matrix. Basically, we are saying A, W, right? So this thing, okay? A matrix, the first row, the first row times the first column, give you the first value, okay? So this is the first value. Right? It's really the first row, A1 something, okay? That's this W. Okay? And then if you look at the second, this is second row times this, which is this one. Right? All the way, you can easily see this part is A. Okay. And if you look at this part, right? So this part is actually A transpose, right? Because you basically swap the I and the J in the A matrix. Okay. One originally on the left hand side, and now go to the right hand side. Okay. So then this becomes A transpose. It's the same linear equation, but now when we do inner product with W, it's the first column. Right? And if you transpose A, then it becomes this. Okay. And the question here. So this conclusion we'll be using in today's lecture. Okay. Yeah. So far what we see is a first derivative. Right? What if we compute a second derivative? Okay. Right. So as we said, second derivative is a matrix, right? Because you can Wj take derivative I and j have 2 different dimensions. So this is called a Haitian. Right? So how to see what is a Haitian matrix? Here we need to go back to the original definition. Okay, so let's go to where we have the definition as a reminder. Okay, so we say that the Haitian matrix is something like this. Okay, so the ith row, jth column gives you a value. So this is this is the ith row. This is jth column. Okay, this value here is really G take partial derivative Wi and then W. Okay? So that's what Haitian matrix is. Okay. A Haitian matrix has a lot of properties we will be utilizing. We will see that later. All right, so in that case, we just follow the definition, right? If you look at here, right, so the ith row and the jth column. Okay? So what we do is take a derivative to wi and then to wj. Right? So first you will take a derivative to wi, okay? And if you take a derivative to wi, so this term is gone. The coefficient is this, okay? And the other item doesn't matter. So the particular item that is your wi, this term matters, okay? So this sum will be gone, only one term, which is for that particular I, because now we consider I as a constant. Matters. Okay, so your coefficient will be something like this. So let me, this after taking derivative, ax take derivative a. So we have coefficient with this sign. Okay, so now we want to take another derivative of this thing, okay, right, to j, and this will become this guy. If we take a derivative to j, the j now also becomes constant. Right? So the other term that is not equal to the particular j is gone. So only one term is gone. And the value is exactly aij. Okay? So you have aij here. Okay? So this is we are considering, we are considering just the assume, this I, this j. So we are taking derivative I, and then let me see how to say this. Yeah. Oh, I was wrong. So we probably should do something like this. Instead of saying I and j, let's call this A, okay, and B, right? So then there will be less confusion because you can easily go I and I here. So now let's think about this, right? We first take derivative WA, okay? So the first probability is I equal to A, right? So WA, okay, WJ, AJ. I think this A and this A are different. Okay, so it's really, so we do this and take a derivative to, take a derivative to WA. Right? First take a derivative to WA, and what will be left is this. Right? So this term, and summation over, summation over J. Okay, and then if you take a derivative J again, right, to B again, so this only one term will be left, A, B. The other not B will be gone. Okay, and take a derivative WB becomes A. Okay, so this is one term. But who tells you first match I to A and J to B, right? You can also have another case that you match it's the other way around, right? To J to A and the I to B. This is also possible, right? So if you consider that case, it will give you, for example, previously we say this is Aij, right? Ij, and the other term will give you Aj. Okay. These terms are all sum, so different cases. Okay. So if you consider this is basically a summation of them, okay? And so this gives you this Haitian matrix, right? And it's not difficult to see that if you can break this into the left-hand side. Right? Left-hand side is basically A. Okay? Right-hand side, actually, let me see. Yeah, left-hand side is A. Okay? If you just take all the left-hand side, okay? Think about it, A11 plus A, basically. And then you have the right-hand side. Okay, right-hand side is A11 again. This is AM1. This is M1N. AN. So this gives you A transpose. Okay, so you can write it actually as A plus A transpose. Okay. So what is this equivalent to? Right? So as we said, this thing is y equal to ax squared. Right? If you take a derivative, it becomes 2ax. And take a derivative again, it becomes 2a. Okay, so this is a quadratic, second derivative. So 2a is a plus a. Okay, and we know this is scalar. Right? You can write a transpose, and they are the same. So basically, they are just a generalization of what we are familiar with in the scalar case. Any questions? I hope this is okay. All right, so in general, so because this course is not about machine learning, right? So we covered these things in machine learning actually earlier, if you took my machine learning course. Okay, so we have so matrix cookbook. Okay, so let me see this link. So there's a lot of this is a formula book basically. Okay, so that's why it's called a cookbook. Okay, and actually in machine learning literature, a lot of people like publishing papers to do gradient descent, optimization, they needed to. So you can do a lot of to the determinant, to inverse. So it can go pretty complicated. Okay, so how to take derivative. This now is a taking derivative matrix element. Okay, and this is a taking derivative entire matrix. Okay, and there's a lot of formula. It's just like in the scalar case, you need to memorize them. Right? So in the high dimensional case, right, it's become more complicated. You cannot memorize all of them. Okay, so we have a book to help you guys. It's like a determinant. This is a trace. Okay, how if these operations on high dimension happens, how do you take the okay? So that's basically something that we you can be aware of. Okay, so this is called a matrix cookbook. Okay, if you let's say you are working with a lot of variables and you are doing optimization and you don't know how to take derivative, you just come here and you find what is the formula you can do, right? And just Google matrix cookbook, you will find this book. Okay, it's very famous. Okay, I hope that this is not too much crazy, okay, because if you are not familiar with those things, it's probably a little bit overwhelming. Okay, but keep in mind, we will not require you to take all of these things in mind. Okay, just the linear form. Okay, this formula you do not want. This formula in the high dimension. Okay, and this is a linear form, and there's a directive form that you should know. Okay, this one we'll be using, including the linear form. And also the second derivative. So the second derivative here, we need to know. Okay. But the others you can be generally aware of. We will not test you anything. So you know there's a tool that you can resort to. Okay, if you go to really complicated crazy stuff. Okay. But so far we are talking about unconstrained optimization. So for example, you have a function like this, and you want to compute the derivative equal to 0, which is a minimum value. Okay, so there's no constraint, right? But in a lot of cases, these x values itself can be constrained. Let's say, hey, you can only take value around here, right? Then you cannot reach here. The smaller value should be achieved here. Okay, so this is called a constraint optimization. And the way to address the constraint optimization is to use the Lagrange method. Okay, and Lagrange method has two versions. Right? So the dual form for optimization. Right? So here we are considering a special case where all the constraints are equality constraints. Right? There are a more general form that it's a inequality, okay, or something like this. But we are just considering a special case of equality constraint. At least for this course, we only need that. So actually, if you take the calculus course, you still remember that the conclusion is very simple. If you want to optimize, let's say minimize this value, okay, for some x, but the x has to satisfy these requirements, right? So the solution is really create a so-called Lagrangian, which is an unconstrained version of this problem. Okay. So the way is firstly you copy this thing, okay, and then you move this constraint. You need, when you change this constraint, you need to make sure that one side is 0. So for example, if you want to make this side is 0, this should be 1. This will be B1 minus G1. Okay. And then once one side is 0, the other side will be constrained here. Okay. And for that, you need to multiply a so-called Lagrangian multiplier. Okay. And you do this for each constraint. So we have n constraint, we have a summation. After doing that, this problem actually, originally you only have x, which you want to try different values and minimize this x value, right? Now, after integrating the constraint here, you introduce so-called new variables, right? Lagrangian multipliers, okay? So this function becomes, x lambda. But you can show that if you choose x and lambda, right, try all the values and you want to minimize this, right? So then this minimized value will be the x that minimizes value will be corresponding to this x when it satisfies this constraint. Okay, so the proof is in calculus course, and I think it's out of scope of this course, but just keep in mind, if you have constraints, what you do is you move to here and add a Lagrange multiplier. Of course, you need to make sure one side is 0, the other side is a function. Okay? And then you address this unconstrained part. Yeah, here's an example, right? So for example, your target function is this function. Right? You want to find those x, y, z different kind of values and try to maximize this. Okay? Try to maximize this. But you cannot just take any x, y, z. Right? So you need to make sure these two requirements are satisfied. For example, this is basically x equal to 3z. Right? So x is 3 times z. Okay? So you cannot just take any values. Let's say it's 1, x has to be 3. Okay? It cannot be 4. In that case, how can we find the best value? Right, so the solution is, hey, first you move this to make sure this is equal to 0 on one side, and then this formula, this thing here becomes one constraint. Okay, add a Lagrange multiplier. Okay, and this constraint becomes another constraint. Add a Lagrange multiplier. You may ask why it's minus, right? Add addition or minus, they're equivalent because these are variables, right? Okay, they are free variables. You can Lagrange multiply, you can negate them. Right? So basically, this can take any value, right? But you want to find a value that minimizes. Okay? Summation minus doesn't matter, right? Because our constraints are equality constraints. If it's inequality, it matters a lot. Okay? And then you just solve for this. So now you have this new problem with two Lagrange multipliers introduced because of two constraints here, right? You take derivative x, take derivative y, take derivative all of these except 0. And then you will find, because there are 5 equations and 5 unknown variables, you will solve for the particular values, x, y, z, lambda. And these values are actually the values that maximize this. Okay, we can show you. Any questions so far? Yeah, so here it's just a recap of the math background. So as long as you can capture out, that's fine. Okay, you don't need to prove it. Yeah, okay, all these are well proved, and probably you already learned that before, but just to refresh your mind. So next is a concept of so-called convex and concave functions. Right. So why convex or concave is so important, right? So here you say that a function f is convex if this happens. Okay, so this is a convex function. Okay, let's say we take any value in the middle. So let's say this is x and y. This is y. This is x. Okay, this is f that dimension. Okay. So this is any point in the middle. If you have any point in the middle, theta to x and 1 minus theta distant to y. Okay? Any point in the middle. And then you take a look at the function value. Okay? You take the f. So you go up to the function value. Right? But you will find that this thing is going to be below if you directly connect these two lines on the function line. Okay? Because this is fx, this is fy. So basically, if fx and fy, you smooth them directly, it's in the middle of the line. Right? And actually, you can show, it's not you can show, right? If you can, let me see, just move. So okay. Here. Somehow, it moved again. Just let me try. Yeah, I hope this time it will not move. Oh, it's crazy. Anyway, so let me see why this is happening. Anyway, okay, so you can see that this is above it. Right? So this is above it. So what this means is saying that a convex function basically tells you that if you are, any value, right? If you put a line into functions, okay, any value of the function is below this line. Okay, this is convex. Okay, so concave is the reverse. Right? So if you have a concave function, then you put any two points and draw a line. the function value is above this line. Okay, that's concave, right? Is it okay with you guys? And if your f is concave, right, minus x is convex, vice versa. Okay. So the nice thing about, because this is scalar case, right? In a scalar case like a y equal to fx, it's a scalar. Okay, we should already know this conclusion because a convex is equivalent to saying that the second derivative is larger than or equal to 0, right? So how to see this, right? Let's consider this is a convex function. Okay, right? And you know, your first derivative is a slope. Okay, it becomes, originally it's negative. Right? This may be -1, it's 45 degrees. Right? Gradually it becomes 0. Right? So if you look at the derivative value, it actually decreases. Okay, the gradient value on this side is decreasing. Right? So, and then if you look at here, this speed up again. This becomes, for example, 45 degree 1. So this increases. Okay. So this is not decreasing. This is also increasing because you know this is -1 all the way to 0. This is actually increased. The negative degree is decreased. Okay, but so all along the way, this is increasing. Right. So if you look at your gradient, this gradient value here, right? It's like this is -1, this is 0, this is 1. Right? So your gradient value is always increasing. Okay, so this is your first derivative, right? So what does that mean? The first derivative is increasing, right? It means that the second derivative is positive. Okay, I hope this is okay with you guys. So let me, right? So this means if you look at the second derivative, right, it's going to be on the positive side. Okay, so that's what it means. This is intuition. Okay, if a function is convex, the second derivative is positive. This is a scalar function. Right. I believe that you know, you should have learned this in calculus, but hopefully you still remember. So this is just a special case where we have the scalar. So in that case, so you know, so what if x is vector? Okay, what if x is vector? So if x is a vector, you still want a second derivative, which is the Haitian matrix. Okay, right? Still want to be positive, but this time it's not simply positive because this is a matrix. How can we define that a matrix is positive? Right? So you can see this notation is kind of like this, right? Not a straight. Okay, it's a curve. Right? So this basically says that this is called the matrix itself is positive semi-definite. Okay, positive definitive you don't have equal. Okay? It cannot be 0. Okay, so we will see what is a matrix is positive, which means positive semi-definite later. Okay, and so in order to show that your function is convex, you either show that its second derivative, the Haitian matrix, is positive semi-definite. Okay. Another thing is that you can follow the definition that we showed before. Right? Just to plot a line, and you want to show that even in high-dimensional space, you can do that. Right? So you show it's curve. Right? So it's a surface. Right? So this surface, okay, if you put two points on the line, okay, it's above the surface point. Okay? In that case, it's a if you follow that definition up there, just think about these x and y as vectors. Okay, if you can show this, just treat them as vectors. Okay, then you can also prove this. Right? If your f can always satisfy this function for any x, okay, for all x. You can follow the definition proof. You can also take the second derivative and show that the Haitian matrix, positive semi-definite. Right? And another important thing is called the convex algebra. Okay, means if you, let's say f is the convex, g is convex, and some operation over fx and gx will still be convex. Okay, so these are what we will see shortly in some slides later. Okay, I think do we have that slide? Yeah, that's the next slide. Right. So another question is why? Why do we care about convexity? Right. So let's use this just simplest y equal to fx scalar x case. Right. If your function is convex, then if you do gradient descent, right, you put a ball here. Okay. Finally, it will go to the smallest value. Okay. If your function is concave, right, if you take the so-called gradient descent, you will reach the next value. Okay. But if your function neither convex nor concave, what will happen is you probably have something like this, right? Then this goes to something really complicated, right? So previously, if you think it's convex or concave, all you need to do is take derivative and set to 0. You know, this is highest point, this is low point. On the other hand, if it's neither convex, let's say here it's above, right? But here it's below. Right? So in that case, the derivative equal to 0 is neither the max value nor the minimum. Okay, you never have any guarantee. Right? So that's where things get complicated. And so if you know that in deep learning these days, you know, we are basically in a non-convex function. Okay. Right. So what we do is also gradient, right? So that's why we sometimes do some momentum, as we described. If you fall here and you don't just hey, if the gradient is 0, I don't move, right? Because they accumulate some momentum, it will push you up and it come down and push you up, come down again. Okay, then you can reach a low loss. Right? So that's the deep learning part that we saw before. The idea. Okay, so that's why they have so many different kind of variants, like Adam, Adagrad, etc. Right? Not the basic SVD. It's the passive descent. Okay, and they are just adding some additional stuff to make sure in non-convex case you can still reach a reasonable result, hopefully. Okay, but if you're convex, it's very simple. Just do gradient descent, or just set the derivative to 0, and this is the point you get a max, best result. That's a minimum loss. Okay, loss function. Any questions so far? Okay, I hope this is okay with you guys. And if this is the case, then, next let's look at what are the operations that will preserve convexity. Okay, there are a lot of them, so we will not look at all of them. Okay? Just give you a feeling of some of the functions that will preserve convexity. Let me see how many pages we still have. We still have 5 pages. I think we can finish by 6, and then we'll take a break. So firstly, if your function f itself is convex, if you time a non-negative weight, okay, usually it's positive, right? So then if x squared is convex, right? Something like this. 2x squared is still convex. It's pretty obvious. You can follow the definition. 2 points and then twice, still above. Okay. Alpha can be 0 though, right? So if it's 0, then the whole thing is 0. Right? It's a constant, okay? Right? Where the value is 0. It's a constant value. It's convex. Linear function both convex and concave. Okay, because our this is because when we define it, we have the equality. Okay? So here we have the equality. We allow it equal, okay? Which means if it's the same line, then the function is also this line, and in the middle it's equal. Okay, for no matter whether convex or concave. So it's the special case where if it's both convex and concave, then it's a linear function. So another thing that you can easily prove is that if you have 2 functions that are convex or a bunch of functions that are convex, if you sum them up, it's still convex. So this is also intuitive, right? If you value the both, then you sum how many of them, both are above, right? So it still keeps the relation. This extends to infinite sum, which means you can sum a lot of them, right? Even integer. This is quite general. Finally, if your function fx is convex, and then you do a chain rule, right? So do another variable that is linear, right? It's still convex. Okay? This is called affine function. So sometimes we call it the linear transformation, right? But usually linear, sometimes the word is reserved to ax, right? It's cross the center. When x equal to 0, the value will be 0. Okay. If you have some bias here, b, it's oftentimes we call it affine. Okay. But they are basically the same thing. You can also call it linear. Okay. Linear. If you see somebody talk about affine, it means this b is not 0. Okay. Any questions so far? So not all of them will be useful, but we just go through all of them. Because then in the next slide about SVD application, we'll use some of them. Okay. All right, so let's look at some examples how to use this theorem. Right? But firstly, let's take a look at this function, right? Okay. So is it convex or concave? Who can answer me? And how you can see that? Okay, so these are what we are using. For example, here, if it's a integrate with a linear function over x, right? So this doesn't change the convexity. Okay, so it really depends on log x. Okay, if you know log x, right? So this is base e. Okay, so log x is something like this shape. Okay, so this is if you put any two lines in between, this is below it. Right? So this is concave. Okay, so you know you can also easily prove it. Right? So for example, log x. Okay, if you take a derivative, it's equal to 1 by x. Okay, and we are saying that x can, you know, when you take log, it can not be negative. It's always positive. Right? So this thing is always positive. Right? So when this thing is let me see. No, we should take a second derivative. Right? So 1 by x. Okay, and then we need to take a derivative x again. This becomes negative x squared. Okay, because this is to the power of minus 1. Right? If you take it again, it's minus 1, and to the power of minus 2. Okay? This is negative. And x squared is always positive. Right? So this becomes a negative. Right? Because this is negative, so we know this is concave. Right? Because we just told you that for scalar functions, if your second derivative is positive, it's convex. Right? It's negative, it's concave. It's okay? Now we know that log x is concave. Right? We have a negation sign here. Okay, you can put it here. Negation is convex. Okay, it becomes some shape like that. Now we know that these terms are convex. We sum them up. Then we are using this theorem. Adding stuff that are convex together is still convex. So this function, you can see it's convex. So these are, we are using so-called the third way of developing this, called the convexity algebra, convex algebra. Okay, you know some functions are convex and some combination of them will still be convex. We'll use some quick way to see that. Another interesting thing to remember is norm function, LT norm, Frobenius norm, Elgaard norm, etc. Norms are always convex. Okay, and so if you norm is convex and you integrate with a linear function, it's still going to be convex. So this function is also convex. Okay. I think I will skip this one. Okay, this is more like a chain rule, kind of how to keep convexity or concave. It's irrelevant to this one. Okay, maybe in machine learning we care about this, but here it doesn't matter. Let's really focus on Quadratic Form. Okay, so there are 3 pages on Quadratic Form, and then we are done. Okay, for the first part of the. Any questions so far before I move on to Quadratic Form? Okay, I hope this is fine. Let me see. Because the attendance is not very good, let's take a comprehensive attendance today. Okay, and then we will continue to second. Okay. And then after taking attendance, we will go back to these 3 slides, and then we'll take a break, 15-minute break, and we will go to the second half where we will look at SVD applications. Okay. All right. So I will call each name 3 times. Okay. If by the 3rd time you didn't reply, so I will pass you. Okay. Joshua, are you here? Joshua? No. Sai, are you here? Sai, am I giving the right?
Yes, Professor.
Okay, got it. Hada.
Yes, I'm here.
Okay.
Hi, sir. This is Kedar.
Yes, I'm calling Hada. Can you see the screen?
Yeah.
Yeah, I'm not calling on it.
Okay. I thought it's my name.
Oh,
So
okay. Yeah.
okay, got it.
Gypsy, are you here?
Yes, Professor, I'm here.
Okay. Sai, Sai Rafi, are you here? Sai Rafi? Sai Rafi? No.
Hey, are you not in class?
What? Hello? Sandy.
He's taking everybody. So first name was.
Yeah, I'm taking everybody. Okay, so you are not muted, Sandy. Muhammad, because attendance.
Yeah, I'm here.
Okay. Hasha, are you here? Hasha? No. Okay, I will call 3 times. Anikat? Anikat? Anikat Ashok? No. Gayatri? Gayatri? Are you here?
Yes, Professor.
Okay. Vashini? Vashini?
Yes, Professor, I'm here.
Okay. Adriana? Adriana?
Here.
Okay.
I'm here.
Got it. Mahesh? Mahesh, are you here? Mahesh? No. Chun Yaochen? Chun Yaochen, are you here? Chun Yaochen?
I'm here, Professor Joshua.
I see you. Okay. Chun Yaochen is not here. Jue Chen? Jue Chen? Jue Chen? No. Qin Yu Chen? Qin Yu Chen? Qin Yu Chen? No. Xu Ping Chen?
Yes, I'm here.
Okay. From
Yes, Professor.
Okay. Pravi, are you here?
Yes, Professor.
Okay. Let me get because of,
Excuse me, sir.
yes.
Excuse me. Sorry, sir. I'm Harsha. My connection is so bad.
Sir, this is Saira. My connection is bad too.
I'm
Okay.
like
Can
getting
you
disconnected.
type on the chat? I will fix that later. Okay. Yeah. Dhamik?
Yes, Professor. Yes, Professor, I'm here.
You're back. You're back.
Yes, Professor, I'm here.
Okay. Achu.
Yes, Professor, I'm here.
Tom.
Yeah.
Got it. Daniel.
Here.
Wood. Class.
I'm here.
Okay.
I'm here.
Okay. Got it. Alak. Yeah.
Yes, Professor, I'm here.
Okay. Bahanutija. Bahanutija. How do you pronounce it? Bahanutija? No. Varan.
Yes, I'm here.
Okay. Taiwan.
Yes, I'm here.
Okay. Sun Tong.
Yes, I'm here.
Okay. Sai Vidwan.
Hi, Professor. Hi, Professor, I'm here.
Philip.
I'm here.
Okay. Swanjo Li.
Yes, Professor, I'm here.
Okay. Peida Li.
I'm here.
Okay. Ming Li. No. Gauche.
Yes, Professor, I'm here.
Okay.
Yes, sir.
Vasha.
Yes, sir, that's me. I'm here.
Okay. Abhilash.
Yes, sir. I'm here.
Okay. Ko.
I'm here.
Okay. Achana. No. Pranav.
I'm here.
Okay.
I'm over here.
Okay. Sonic Q.
Oh, we got 2 more participants.
Are you here, Sonic Q? Just the one confirm. Sonic Q, can you repeat?
Yeah, I wouldn't mind.
No. Okay. Aditya? No. Saga?
Hey, Professor, I'm here.
Okay. Harish?
I'm here.
Trent was like, my savior. Dude, I'm in the call. You are the man.
Devanshi? Are here?
Yes, Professor, I'm here.
Okay. Santosh? Santosh, are here?
Yes, sir, I'm here.
Okay. Khadija? Khadija?
Oh, shit.
Khadija? Yeah, Woodfin, so you are not muted. Okay. Khadija? Khadija? No? Professor.
I'm here, sir.
Okay. Sandy? Sandy?
I'm here.
Okay. Tom?
Here.
Okay. Taylor?
Hello.
Okay. Say Li? Say Li?
I'm here.
Okay.
I'm here.
Zhang Si? Okay. Shravan?
Yes, Professor, I'm here.
Okay. Madhu?
I'm here, sir. I'm here, Professor.
Carmen?
I'm here.
I see the tennis is jumping up. Okay, somehow. Bilawal?
Yes, sir, I'm here.
Okay. Katha?
I'm here.
Okay. Boniface?
Here.
Okay. Piyush Sony? No? Corner?
Here.
Okay. Sushmita? Are you
Yes,
here?
Professor, I'm here.
Okay. Zhenzhitan?
Yes, I'm here.
Sushmita?
I'm here, Professor. I'm here.
Okay. Quentin?
I'm here.
Okay. Brandon?
I'm here.
Okay. Amulia? No. Kalyani? No. Freya? No. Hamid?
Yes, sir, I am here.
Okay. Yuji Wang?
Yes, I'm here.
Okay.
I'm here, sir.
Ziming Wan?
Yes, I'm here.
Okay. Frank Wu?
I'm here.
Okay. Jing Wu? Jing Wu? Kranti?
I'm here, Professor.
Okay. Ran?
I'm here.
Okay. Abhisha?
Yes, I'm here.
All right. So I heard some panic sound somehow. Okay.
Professor,
Sir, Banu Teja, sir, Banu is
Professor.
Yeah, if you want to fix attendance, because I see attendance boosted somehow, okay, close to 70. So if you previously was just
Professor.
yeah. So
Professor Sairashi.
yeah, can you just type on chat? I will fix that later. Okay, just type on chat. Okay. Okay.
Professor, I'm here.
Okay, got it. All right. So what's the time now? Okay, we did a comprehensive attendance. Yeah, let's take a 10-minute break. Okay, I will fix the attendance here, and in 6:15 we'll be back. Okay, and I will be here. If you have any question, just let me know. Okay. Okay, so I will. If you pass that, I will take a note. Okay, so basically, I will fix that, but you will not hear after 3 calls.
Hello, sir. I'm Harsha, the one.
I understand. Yeah, I'm fixing one by one. Okay.
Due to this rain.
Just type on the chat. I will. Since there are lots of them. Okay, so I need to go one by one. Okay.
Sai Nikhil, sir. Professor.
Yeah, but I'm following the chat. Okay, so because I'm searching. Okay.
Hello, Professor. I'm present here. Kalyani Odapelli.
Yeah, but I'm following the chat. If you just type on the chat, okay? I will fix it.
Professor, yellow means it's partially present or like it's green, right?
Yeah, so we will count you this time, but there's a record there. So potentially because of the attendance, because the first time we called it 3 times. Okay, so we will keep a record. Okay, but this time we will not do that much. So we can flip back if you like. It's always like this multiple times. Probably we will do that much. Okay, because we probably cannot count it. But this time we will count. Okay, so we do want to differentiate.
Professor, I was actually there, but I couldn't speak. I was since there, like the beginning of the
Professor,
class.
I responded few seconds after you called my name. And I even texted on chat due to the microphone problem.
Yeah, so again, I will not do that mark this time. It's just
Same with me as well.
Yeah,
Professor.
I just like sent you the chat right after you pronounced my name.
I understand. So this time it will be the same basically. Okay, so it's just a different notation. So if you wanna you don't like the notation, just so if you are already here at the beginning, just let me know.
Yes, sir. We are here from the beginning, like from the starting of the class.
No. Yeah, me too.
Yes,
me too,
sir.
Professor.
Sir, even
Yeah, Professor.
Harshavardhan Reddy, I was here from the beginning, sir, but due to this connectivity issues, I was going. Yes, sir. Thank you, sir.
Sir, Banu Teja, Pullapalli.
Okay.
So,
I called you multiple times actually.
but actually, I was speaking, but I couldn't hear. You couldn't hear this due to a network issue.
Me also, Professor Sai Nikhil Palagati.
Hello, Professor.
Yeah, but
Amulya Valpadasu.
yeah, I actually
Sai
multiple times actually. So.
Oh, yes, I was saying.
Yeah, it's okay. So because we will count this as a canon, okay, but just to keep a record because the first time you did. If you really just
I was there. I typed in chat as well, Professor Sai Nikhil Palagati, after the moment.
So I will continue.
Yeah, me too, sir. Aditya Pampana.
Me too, Professor.
You can check the chat as well. Like the time which you took my name, I have dropped the message.
I see. Okay. Yeah, so we will come back maybe 6 minutes later. Let me know if you have questions.
Sir, Amulya Valpadasu.
Okay.
Professor Aditya Pampana.
Who is talking?
Aditya Pampana.
Yeah.
You took my name thrice and then I dropped the chat because you were not able to hear it.
Can you spell name again?
Aditya Pampana. ADI.
ADI, okay.
TYA.
Sambar, I guess.
Yeah.
Right. Okay.
Sir, do we have a class tomorrow? As
Thank you.
On our canvas, it's shown that we have a class tomorrow from 3:30 to 4:30.
Are you talking to me? 3:30.
Yes, sir.
We have a class 3:30 to 4:30 tomorrow.
Yes, sir.
I think it's a weekly class, right? So today is a class, right? So
Today is our class, but on our canvas, it shows that tomorrow too we have a class from 3:30 to
Professor
4:30.
Kalyani is present.
no, we don't have class tomorrow. Okay, so this is
Okay.
Yeah.
so good break last time.
Thank you.
Hello, Professor. Am I audible?
Yes.
Yeah, my name is Mahesh. Regarding my attendance, actually, I couldn't say yes for the first time when you called out my name.
What's your name again?
Mahesh Bansar.
I remember I called you multiple times. Right. I think this is already counted in. Okay.
Yes, sir.
Okay. Yeah.
I was present though from the beginning of the class.
Yeah, I trust you this time. Okay, but apparently this time the attendance is totally different from when before I take attendance. Okay, but I will come to that. Okay.
Professor Amulya, I have texted you, sir. I've mentioned in the chat.
Okay. This is you, right?
Sir, Piyush.
Yes, sir.
Okay. Who was talking?
Piyush, sir. P-I-Y-U-S-H.
P-I-Y-U.
Professor Kalyan.
So were you here? Because I called multiple times.
Sir, I had
Excuse
some
me?
meetings, so I was disconnecting regularly.
No, if you are disconnecting, there will be a sound like disconnect. All through the way I didn't hear. I will come to you.
Excuse me, Professor.
I was sir online with my roommate Santosh laptop. He's also in.
Excuse me, Professor, I have a question.
Yes, what's the question?
There was a class trying tomorrow, like at 3:30 to 4:30. What's that?
So where do you see that? Just
on Canvas. It's saying tomorrow, March 24, from 3:30 to 4:30.
So on Canvas announcement or
yeah.
Let me see.
Yeah, on Canvas calendar and announcements. Yeah, it is showing us. Isn't showing on my dashboard, basically.
Oh, really?
Yeah.
I don't know why this is happening because I didn't configure anything. But
can you look into that?
Yeah. But I can't see anything showing that. So this is our latest announcement. I didn't send any announcement because this is the annotation. Okay.
Can I send you a screenshot?
What?
Can I send you a screenshot of that?
Yeah, please.
Announcement.
Yeah,
okay.
Send by
just a second.
I can take a look. Thank you. Yeah, because there are some multiple students talking about it, so we need to fix that.
Chat me, please, screenshot.
Hey, you know my email? Just send to.
Yeah, I know your email.
Okay.
Yeah. I'm emailing you.
Mm-hmm.
I'm emailing you the screenshot of that.
Yeah. Thank you. Just attach the screenshot.
Okay.
I think we haven't finished the other one. So I see Anikat messaging me, right? So were you able to chat previously? Did you type on chat previously? I cannot find it somehow. I can count you in this time, okay, but because I cannot find it, it's already counted in, right? So it should be okay. Okay, let's begin. So I see most students are joining somehow.
Hey, Professor, this is Kalyani here.
Mhm.
I was present from the beginning, but due to the network issues and the mic problem, I couldn't give my attendance.
Can you type in the chat? I will look at later. Okay.
Professor, I'll send you the email. Can you look at it?
Yeah. Somehow I cannot open the email. Let me see. So I can make you a co-host so that you can share the screen and show what's happening there. Would that be okay?
Okay.
Because image is not coming up. Because I can
Okay.
see what I see. Okay, so this is what I see. Okay, I cannot see the image. Okay.
Okay. Okay.
Yeah. So I don't know why. But yeah. So maybe you can try to send again. So tomorrow we don't have class. I don't know why Canvas is the class. Okay, there's no class tomorrow. This is a class. Okay, today. We don't have a class tomorrow. Yeah, maybe there's some mistakes in Canvas. I don't recall we configured anything. Okay. Sometimes Canvas can go wrong or even offline. Okay. So tomorrow we don't have class. Just to confirm. Our class time never changed. Right. So let's continue. So here we are talking about the directive form, right? So I see students are leaving. So as we discussed earlier, right? So this is a quadratic form where we have an x, then we have a matrix, and we have a column x again. This is a row x. Okay, and we can write it like xi, xj, right? So the i's x and the j's x here. Okay, associated with the coefficient here, which is aij, right? So this is called the quadratic form, right? And the equivalent form of the scalar case is this like a coefficient and x squared. Okay. Because if you write a scalar form, it's a x times a times x. Okay, it's the same, right? And this is called a quadratic form, and we can actually assume A and A transpose are the same, which means we can assume A is a symmetric matrix. Okay, if that's another case, we can do the following transformation. Basically, we take A and we take A's transpose and we sum them up and divide by 2. And we can show that they are equivalent, they are the same value. The output, the result value. Remember, quadratic form gives you a value. Okay, it's a scalar. Right? This value will be the same. So how can you see this? Right? So keep in mind, originally, maybe you have, remember you have, when you take a transpose, right? So originally you have, for example, here, this value is aij, okay? aij, xij, okay? And then you have another value that is symmetric, right? So probably here, okay, you have aji, okay? aji, xjxi, which is xjxi, xij is the same thing. Okay, so there are two terms can merge because the xi, xj are the same. Right? It's really the coefficient summation. Okay. Now what you do is you make it symmetric by instead of these two terms become aij and aji, you kind of sum them up and takes the average. Right? So it's like aij plus aji. Okay, divided by 2. Okay, and then you place the value both here and here. Okay, that's what this is. And their summation is still the same. So this term, the coefficient summation of the two terms are still the same. Okay? But the nice thing about it is that after this operation, you normalize it, become a canonical matrix. This matrix is symmetric. Okay? If you cannot see that, you just think about this thing, take transpose. Okay? So A transpose is A transpose. A transpose is A itself. So you can see that after taking transpose, this thing is still itself, which means it's a symmetric. Okay? So no matter initially what is a matrix, you can always take that matrix and do this operation and get the same value, but it's a canonical form. Right? So this is more like, if you have ax plus by plus c, x could be x plus c. You can write a canonical form like ax minus something, like d squared something plus c. Okay, so you can kind of using a canonical form. Okay. So we'll assume that this matrix here is always symmetric. If not, you can just do this. Right. Now, if we think only about this kind of canonical form, then we can show that this is unique. But if you think about this, spheres can only be symmetric matrix. Okay. And now, if these two values, you take two matrices A and B, which are both symmetric, and you do the quadratic form for any x their value is the same. Then the only possibility A and B are the same matrix. Okay, we can show that. Is this okay with you guys? Again, we are not proving much. We are just telling you the conclusion. Okay. All right. So next is quadratic forms. Okay, I see a chat. So yeah. So if so I will fix the attendance issue. Just leave a message, and I will check whether you are still here at the end. And if you are still here, I will kick you. And so quadratic form here we are assuming the canonical matrix here, coefficient matrix. Okay, suppose A equal to A transpose. Right. So then now we can define this. Okay, we have this concept when you say that this matrix is non-negative positive. Okay, and this is called semi-definite. Well, semi means you can equal. Okay, another is you are strictly positive, which is a positive definite. You have no stem. Okay, so what is this? How are these defined? So we are saying that if you have a matrix and then do a quadratic form over the matrix. Okay, if for any x vector you can think of, this is larger than or equal to 0, right? Then this matrix say it's a positive matrix, or we say the positive semi-definite. Okay. Additionally, if this equality can be removed, right? And then this is a strictly positive. It's definitely positive. It's not semi. Okay. But there's a special case that x equal to 0. If x equal to 0, the quadratic form will always be 0, right? So we don't consider this degenerate case in the middle, in the origin, right? And if this is happening without anything that is not 0, okay? If that is the case, then we will everything else, it's not in the origin. This will be strictly positive. Then we call this A matrix is strictly positive. We call it a positive definite. Okay. Again, as I said, so I think there's a attendance thing. So if you have attendance, like because we currently have some boosting attendance. Okay. If you are still here at the end, I will see the chat. You chat, and I will take attendance again on these that you chatted. If you are still here, then I will fix you. Okay. Right. So now let's take a look at what this means. Right. So we are saying that just think about this two-dimensional case. Right. So we are saying the x is a vector of only two elements. Right. Because this is easy to visualize. Right. So then you have the quadratic value. Right. This is the quadratic x transpose A x. Okay. This x is a vector of x1, x2. Okay. Then let's think about it. Firstly, you can see that in the origin, these values are pinned at 0. Okay, pinned at where your fx value is 0. So this is very easy to understand. Because if you look at if x is 0, your entire term can only be 0. Okay. So now let's take a look at what does it mean by positive definite. Positive definite means in this case. Okay. Not only this point you are 0. Okay. If you take any other x or y values here, your quadratic form will be strictly positive. It's above this plane. This plane is 0. Okay. You are positive. Okay. Another concept called a negative definite. Right. So negative definite is saying something like this. Right. So if you change this sign from larger than to smaller than, okay, so then this becomes negative definite. Okay. Something like here. Yeah. So remember this, if you are at the origin, it's always 0. So this is the 0 plane. Okay. And if you give any other value to this is the negative definite. Okay. And there's also a concept called like a positive indefinite. Right? So or we say it's like a semi-definite. Right? So what does this mean? Okay. Right. Here you can see beyond the origin. Right? So some other values along this line, quadratic form is still 0. Okay? This is the 0 term. Right? So in this case, it's larger than or equal to 0. Okay? So this is basically we are talking about something here. Right? Okay. And in this case, we say that this A matrix is positive semi-definite. Okay. And the tricky case is here. Right? So if you are 0 here, but sometimes you're positive, other places you are negative. Okay. If that happens, then you are neither positive semi-definite and nor positive negative. Okay. So why we care about those things? Right. The reason we care about those things is that we want to show this. Right? If you have a function that is over a vector, you compute its Haitian matrix. And this is a Haitian matrix, and then you show if this matrix is a positive semi-definite, okay? Then you are convex. Right? And then if you do gradient descent or take derivative to 0, it will be the optimal value. Okay? You can reach the optimal. Otherwise, there's no guarantee. Okay? Even though you can use like add-in, those kind of methods to achieve that. Hopefully, you achieve the lowest value. There's no guarantee. Okay? Yeah, so these are the preliminaries. We are not using all of them. Okay, but just to keep in mind how to take a derivative, especially for linear form, which is here. Okay, we will use these conclusions later. Okay. It's linear form, and this quadratic form for if you do second derivative. It will be, okay. Keep in mind of those conclusions that we will be looking. Okay. Next, let's look at the SVD applications. So it has been 2 weeks, right, since last time we talked about SVD. So we will have to go through some recap. Okay. So we told you that before SVD, we have a concept of Eigen Decomposition, right? So Eigen Decomposition requires that your matrix should be special, okay? It should be a real and a symmetric matrix, okay? Oftentimes, positive semi-definite, right? So it's for example, covariance matrix. We will see what is a covariance matrix later, okay? If that is the case, right? So if you can have real symmetric matrix, right, this has to be symmetric. The ij, ji, the value should be symmetric. Okay. If that's the case, you can do this kind of decomposition. Right? And it's just like SVD, right? So you can show that on the diagonal, okay? So these values, you can write this equivalently like this. Okay. Last time we showed how to do it. Okay. And if it's a real symmetric values, those DRI will be real values. Okay. If A is again positive semi-definite, like a covariance matrix, we will see those things later. Okay. These values will be strictly non-negative. Okay. It can be positive and become smaller all the way to 0. Okay. So what does this mean? This means it's kind of similar to singular values, right? So it's called the eigenvalues, but it's very similar to singular values. That's why you are doing PCA, you take out the small values, since they are noise dimensions, you only take the first few principal components, okay? In the PCA, you will see that. So this is called Eigen Decomposition. And we know that Eigen Decomposition, initially the definition is following this one. Right? So if you have a vector, which is an eigenvector, okay? And you do a linear transformation over the eigenvector, it will give you an output vector, which is on the same direction, but maybe scale them or in the opposite direction. Okay? So this is Eigen Decomposition. We also said that there's another concept called SVD. Right? So this is what we see earlier, right? And A is a rank R matrix, and then you can write it like this, or you can write it like this. Because it's rank R, you can sum all the way to R components. Okay. And how you derive this to here, we also showed. It's equivalent to this. So the logic is the same. It's the only difference in U and V in Eigen Decomposition. It's the same thing. But in SVD, they are different. U and V are different. But both of them are orthogonal. Okay, P is an orthogonal square matrix, but U and V are orthogonal matrix. It doesn't have to be square. So U is kind of these vectors, column vectors. V is a row vector. Of course, we are talking about the row V transport. If you look at V, it's again column. Right? And the equivalent form to this is saying that if you have a V, which is the dimension we find, right? So the dimension we find, 1 back 2, that's a major dimension. Okay, and then do a linear transformation. It will give you the u direction instead of v. Right? So the left singular value back 2. Okay, or scaling it by the singular value. Okay. On the other hand, if you do the transpose operation, right, and on the u, you will get v direction. Okay, so this is equivalent to this in some sense, but it's different. Okay. Another important difference is that SVD works for any matrix. Right? Okay. While for Eigen decomposition, it has to be a symmetric square matrix. Symmetric means square, because you have a diagonal. Okay. Any question about this recap? I hope it is okay. And we told you that, you know, if you have these R dimensions, right? If you remember how we find those VIs, right? We'll find the best dimension first, and then V2, which is also V1, among which we will find the best V2. Okay. And so if you do this for K times, just take the first K component. This is the best fit K-dimensional subspace for all the rows of A. Okay. The A here, when we talk about SVD, are n rows, which have D attributes, D columns. Okay. Any questions so far? If not, we will continue. Okay. Right. So here's how we find those V's. Right. So we will find firstly the best V that maximizes this value, this singular value, first singular value. Okay. And then we continue to find the when you find the case, right? Okay. You want to make sure it's orthogonal to the previous dimension. Okay. And then you can define the singular value of the case singular value. That's this. This chain is maximized. But also vector should be orthogonal to the previous dimension. Okay. Right. Here are the definition of those things. Right? So V1, V2, Vr are the right singular vectors, and these are the single values. And left singular vectors are defined like this. And then we show that you can put them together and you get the SVD shape. Okay. Any questions so far? Okay. I hope you still have a fresh memory 2 weeks ago. Right. So this is just a recap of the properties, right? So if you do a linear transformation of A, so it's A matrix, that you do SVD with the right singular vector. It gives you a vector in the direction of the left singular vector. Okay. The ice. Okay, and as to transpose, it will reverse. Another important thing to see is that keep in mind, right? A may be, for example, M by D dimensions. Okay, but you can construct a square matrix by time this, for example, with this A transpose. For example, if you time with A transpose D by N, right, then you get a M by N matrix. If you do the A transpose times A, then you get a D by D. Okay? So then this becomes a square matrix. Right? This is also symmetric. If you do the transpose here, right, you will first go this direction. First the A transpose and A transpose transpose. Okay, so it's the same thing, which means that it's symmetric. Right? Now let's look at this one. Right? So we think about this matrix as B, right? Just like how we do the power iterations, power method, okay? To compute the singular vector. Okay? You think about this matrix B. Okay? Then what if we time B with VI? Remember, VI is the A's right singular vector. Okay? Then you can treat this. For example, if you look at here, these two AVI. But AVI, we know it's a sigma AVI. Okay, we put it here. And then we still have A transpose here. And this is a constant. You can move up to the front. If you move this to the front, then you will have A transpose UI. Okay? And we know A transpose UI gives you sigma idea. So you move this around and move this to the front. Okay? And this thing is equal to sigma. Right? And finally, this sigma 2 becomes sigma squared. So this becomes sigma squared. And these things are not important. The important thing is you see a matrix B has VI equal to a value as positive value times VI. What does that tell you? What does this tell you? This tells you that it's Eigen decomposition, right? So of the B matrix. Right? Because a vector times a B matrix, right? The linear transformation of the vector gives you another vector that's along the same dimension. Okay. Is this clear? So this basically says, this value here, sigma I square, are eigenvalues of A transpose. Okay, and the VI, the right singular vectors, are the eigenvectors of A transpose. Okay? You can do the reverse. So the reverse is also can be similarly derived. For example, if you do this B matrix times UI, so we know that ATUI is sigma IVI. So it's ATUI becomes sigma IVI, right? And then you can move this to the front. You get this thing, right? And then AVI is actually this one equal to sigma IVI. Okay? So you can see that. And this becomes sigma squared. The only difference is UI, not VI. So UI. So the conclusion we get is this. So you know, again, sigma I squared is also the eigenvalue of this matrix, but also a negative of this matrix. So this is actually the theoretical background of PCA. So the PCA is constructed so-called Coherence matrix, very similar to something like. I think it's probably this Coherence matrix, very similar to this, D by D matrix. How these different variables, right? If you think about D dimensions, right? So data have n rows, but they actually have D variables. Okay? How different pair of variables are correlated along all the n values. Okay? So this is the foundation for doing GCA. Okay? When you do A SVD, it's equivalent to do this covariance matrix. Okay, then do PCA. To do the Eigen Decomposition. Yeah, the same thing. Okay? PCA we'll discuss it shortly. Any questions so far? Okay, let's continue. Again, this is D by D matrix, this is n by n. So firstly, in our previous derivation, we actually did mention that we should actually center the data. Center the data means, let's say if you have data points like X and Y, but your data points is something like, if your points, so let me use, if you have a bunch of data points that are here, then it's not good. Okay, it's not good. You want to move them along this direction. Okay, along this direction. So finally, it's something like now your data points move to this. Move to this region. Okay, and they are centered. Okay, the reason is very simple because if you look at this, the angle will be very small when you choose lines. So which V1, V2, V3 are actually starting from. Then it's not sensitive. This angle is too small. If you move to here, all around, you can get the data. So this is the bad way. Okay, you first center the data. Okay, center to the centerpiece. Okay, what does the centerpiece mean? So if you look at each dimension, let's say this is the x1, x2, x3. Right? So if they are centered, then they are x1, x2, x3, x4, sum up to 0. Okay, basically if you have 1 here, you have -1 here, they cancel. Okay. And similarly on y dimension, on the other dimensions, it's the same. So if you center data, then you do SVD. That's the right way. Okay. So here we are saying that we want to minimize the sum of square distance from AI to SK. That's why we are doing SVD, right? And remember AI here, we are talking about the ith row, obviously the data points, d-dimensional data points of the matrix. Okay. And SVD finds the best fitting subspace, but that condition on that data is centered. Okay. What if the data is not centered? Like we will see earlier, right? It's moving away from origin. It's far away from origin. Okay. Then we can show that. So this is what we want to show. Okay. So if your data is somewhere here, okay, then the SK that minimizes some square goes through the central data point, right? So let's say your data point center is here. This is your central, right? So actually, your subspace should be, goes through the central, right? So it's like you move it here, okay, right? So you do want to center. Right? So this is the center of the data. This is the central replication. So how to see that? So basically, you can see. Let's assume the data is not d-dimension, just 2-dimension, right? So basically, this is saying you have data points like let me x1, y1, okay, think the color is not good. I lose control of them. If you have x1, y1, x2, y2, and you have xn and yn, okay? Something like here, right? So here, each AI, A1 is this, A2 is this. So we are basically computing something like this. Right? So we are computing, taking the average. Okay, so we are saying, hey, this is n, summation of x1 all the way to xn. Okay, this is the first dimension. The second dimension n, y1 plus y. Okay, and you can show that this is central. Okay, if you plot on 2 dimensions, this goes all the way to d dimensions. Okay, is this clear? This is how we define the central. Okay, so if this is okay, let's first think about the special case where we only have k equal to 1. Okay, so which means so this is just a v1. So this is the first dimension. We reduce it to 1 dimension. Okay? In the other case, you can think about it, right? So this is your v, the direction, the unit vector. Yeah, thinking about it. Okay, and this is your a. We are saying that the best subspace must be passing through, if you have the points here, so how do we show that the best? Let me I think there's another diagram that's more intuitive on the next page. Okay. Let's assume your data point is not centered around here, but here. Okay. Then actually the best fitting subspace is gonna be this space. It passes through the center of your data point. Okay. But it's equivalent if you center it around here and then you do the SVD, regular SVD. Because we are now, if you remember how we derive the SVD, we are talking about V1, V2, V3, etc. Right? So they are starting from origin. Okay? But if you are thinking about starting from here, then you need to add some bias, okay? Which was not in our previous derivation. Basically, if you look at our previous derivation earlier, we're assuming your vector starts from origin. Okay? You don't need to add a bias. Now let's think about the special case where we have a line, okay, and we want to show that let me see what we want to show. So here's for example, in 1-dimensional case, right? So the subspace is the line, okay, in the 2 dimensions. Okay? But which line is the right subspace, right, to do the dimension reduction? And so the v direction. Okay? We want to show that this line will pass through the center of the data. Okay, this is what we want to assume. But let's assume now we have this line. Okay, this line is defined like this. Right? So you have a particular point on the line L, okay, which is this point. It's a vector. Okay. Now you can also the direction of the line, which is this v unit vector. Okay. Then you can represent this line in this shape. Okay. How can you see that? Right. So this is actually very simple. So this is A is this vector. Okay. This lambda v is some vector like this. Okay. And then this gives you this vector, which ends at this point, which is on the line. Okay. If you change the lambda, it basically this point will then go to here or go to here and go through all the line. So it's not difficult to see that this actually represents the entire line. Okay. Additionally, we want to say that, assume you have the ith row in your data point. Right? This is your ith row. Okay? Your distance to the line. Right? So this is the line you have here. Here. The distance to the line is this one. Okay? So this is your distance to the line. And additionally, you also have, your component along the line. And so because this is a line, and if you do a cosine theta, then this is your distance. Okay. So we are saying, hey, this thing is this thing. Okay? And this thing, right? This thing is actually this thing, because it's v is a unit vector. If you do inner product, okay. It's like a ticket cosine theta. Okay. So then we know that because this is perpendicular, right? So we know this thing square. Basically, we are saying that this edge square plus this edge square equal to this edge square, okay? Because this is 90 degrees. Okay. So this edge square, which is this thing here, okay. And if you look at this, this, projection square is we are talking about this. And finally, it's equal to the, it's equal to this thing square. I mean, it's equal to this edge. Okay. How do you represent this edge? Apparently, you can use this. So if the minus of 2 points give you a vector, something like this. Okay? And this vector's length is this edge. Right. I hope this is okay with you guys. Right. So this thing is this thing squared. This thing is this thing squared. Equal to this thing squared. Any questions here? If not, let's continue a little bit. Okay, so today is a little bit math heavy. Okay, hopefully, yeah, you can catch up. All right. So next, let's assume that the data point has been centered, which means that sum up to 0. This 0 is a 0 vector, which means, previously we show right x1 plus xn divided by n is 0, which means x1 plus x2, all every dimension, if you sum their coordinates is 0. Okay? So we can just center by subtracting the center. Right? So we shift them to the center. Okay? Let's assume they are already centered. And in this case, now let's first think about what is this. Okay. So we have n rows, right? For each row, the distance to the line L, which for each data point AI, right? So we have a distance. Maybe we have another AJ. Right? So we sum their distance up. Okay. And how can we compute it? Using this rule, right? So if you this thing equal to this thing square minus this thing square. Okay. So basically we have this. Right? As and by the way, this basically measures the, if you remember, this is our how far away each point is to the line square. Okay, this is exactly our metric when we choose a beat. Okay. It's remember we talked about x square. This is exactly this. Okay. Distance. Okay, so now we can write it out like this, right? So firstly, how can we see this? So firstly, what is this? I have a significant delay when doing this. So this thing is, you can, maybe it's not easy to see, but actually we have this here, x square. This thing is equal to x transpose times. Okay? If you cannot see that, just think about this x vector. X vector is like maybe something like x1, x2, xn, xd. Okay? So what is this? This is inner product. This is x1 square plus x2 square plus x2 square. Okay? And what is this? This is the vector length square. Vector length square is square root these square sum, and then take square, take out the square. So they are equivalent. Just following definition, you'll see. And based on this reasoning, we know that this thing here is basically AI minus A transpose. Oh. Let me clear this a little. So this thing, sorry. Thank you. So this thing here is basically something like AI minus A transpose. AI. Okay. Oh, you can write this inside. Transpose. Okay. And this gives you 4 terms. Right? The first term is this term with this term. This gives you this. Okay. it's the same, just like we said. And the second term is this term with this term. Okay, this gives you, AI transpose minus A. Okay? The third term is this term with this term. This is minus A transpose. Yeah. Okay? And finally, it's this term with this term. Okay? This gives you this minus minus becomes this. Okay? And A transpose A is the vectorless. Now let's look at these two terms. They are the same, okay, because it's an inner product between AI and A. Okay? It's the same. So it's minus 2 times this. Okay? So this is how we get from here to here. Okay. Any questions? And then we minus this term. Okay. Let me clear this a little bit. So now, we want to put in the summation. Okay? Now this summation can be put into each term. Okay? This term, of course, this AI has index I, so we can write it like this, and then we put the summation over here. Here it's irrelevant to I, so we add this thing n times. So we have n, and we add this thing also to here, because this is linear, right? Inner product is linear, right? So it's basically, A transpose A. Okay, you can take this out, and the AI can be a solution. Okay, and finally you sum this to here. Okay, and if you do this, it's basically this. Right? So what's interesting here is that we already centered the data. Okay, if we center data, this thing is 0. Okay, so this term is gone. And if you agree with this, then basically, this term is gone, then we only have this term. Okay. So let's look at when we minimize this term. Right? These are the data rows. Okay, you cannot minimize. Okay, this AI you can also minimize. Right. So V is the particular direction you want. Right? So no matter where V is, right? So your A should be 0. Okay, your A should be 0. Then this term is gone, because this term is at most 0, right? It cannot be negative. Okay? So it's minimized when A is 0. Okay? So what does this mean? So let's come back and look at what is A. A is exactly the point on the line. When A is 0, which means this line passes through the origin. Okay? So after you center your data like this, and you can show that this line passes through the origin. Okay? If you don't center, this passes through your central. This is what we do. Okay. So only when you pass through these things, then you have the guarantee that this thing, sum of the distance to the line is minimal. This is exactly what we want. This B direction. Okay. So here it doesn't matter which B we have, right? So which type we have, we always want to be centered. This will minimize, this sum of distance. Okay. So we are saying that really you should pass through the center. Okay. Or if you center the data, so then you pass through the origin. Without centering data, it's going to pass through the center. Is this okay? I know it's a little bit complicated. I hope this will be. So far, we just look at one dimension. That's the first V1. It's only one. Okay. What if we are having the general case that we have a lot of these? Okay. So basically, starting from this origin like A, but you have V1, V2, V3. Each have some components. So here we are saying instead of just far away from the origin, instead of just one V, you have another V2. Right? So basically, it's a surface. Right? You can think about like this. Then we have something like this. We have this can be k dimensions. Right? And so if we have the first k dimensions like this, right? And the V0 is the translation. Okay. So we can derive something similar like before. We can show that V0 should be 0. Just like here, we can show A is 0. Okay? So why? Because these V's are orthogonal. Okay? They are 90 degrees to each other. Okay? If that's the case, if you look at the previous derivation, A will not change. This A becomes V0. Okay? The only thing that changed is here. Okay? This V. Right? Originally, we only have one term. Now you think about it, we have another term here, right? Then basically you have to the mapping to this surface from this A to this surface becomes this one. Becomes their summation of A squared plus B squared. Right? Originally, we only have A squared. Okay? So basically, this term now becomes a summation of the K terms. That are orthogonal. Okay? And if you look at here, this term is this term, right? And this term and this term. But it doesn't impact the fact that V0 should be 0. So the proof should still hold. It's okay? So now just the difference is the summation over this, okay? Instead of just using one term. But this doesn't matter because we still want A to be 0. Okay? The conclusion still holds. Any questions? Right. So previously, if we look at how we define, right, in the last lecture, how we define these VIs. Right? So we are considering everything should pass through the origin. Right? Because if you V is 0, this thing is 0. Okay? So now we say that there could be a bias, right? But if the bias is here, but in the meanwhile, we still want to minimize, minimize this sum of distance of each row to the line. Okay? Then we also have to make A0, which means you have to center it. Okay? Anything that is not centering in the centroid, this line not passing through centroid, will increase this value, sum of distance. Okay? And this carries over to K dimension. Right? So this is if you want me to choose a VK. Okay, so that basically tells you that our previous derivation, assuming V0 is 0, actually is meaningful because if it's not 0, you can only increase this part, okay? which doesn't make sense because this part is essentially this part that we want to maximize. Okay, so no, it's actually something like this. Okay? So this part is a mapping. Okay, so actually their sum is a diagonal. So here this part is what we want to minimize. Okay, we want to minimize that, but it's equivalent to maximize the other part, right? Because one is distance, one is this is the distance. This is distance. Previously we are saying the mapping is this one. Right? They sum up to a constant. Square sum is to a constant. So you want to minimize this sum of square of this, you maximize sum of square of this. Okay, which are basically this is what we derived last time, which are basically this thing. Okay? We maximize this thing is equivalent to we minimize this. Okay? And we show that no, only when A is 0, you will minimize it, which means no, A should be 0. It should be equal to the origin. Okay? And this is conditional on that you already centered the data, right? Which means the origin is central. Okay? If it's not, if you put it back, then this line should pass through the center. Okay? If you don't pass through the centroid, you can only increase this value, which means you decrease the other value here. Okay? This value, which means it's not the best line. Any questions so far about this conclusion? All right, so long story short, when you cope with data, first center your data, okay? After centering the data, then you do this kind of dimensional reduction and the processing, etc. Okay? This is actually quite often the case in machine learning models. So let's look at the PCA. PCA is a one-dimensionality reduction method. Okay, it's actually highly relevant to SVD. Okay, so if you look at SVD, it's directly operating on A. PCA is equivalent, but it's operating on your A transpose. Okay, so as we just showed earlier in the slide, okay, in this slide, So your SVD directly on A is equivalent to PCA over this, okay? To Eigen Decomposition with Eigen Matrix. Okay? So we are directly over this, which is D by D dimension. It's how, let's assume this is the n rows of data rows, right? Each have the different variables, so 1 all the way to xd. How different columns, different attributes are correlated. So this is the D by D matrix. Okay? The ith column and the xi and xj, how they are correlated. Right. So the only difference is that PCA is operating on the covariance matrix. Okay. We will see that shortly. So again, let's think about this data matrix A. Here we are calling it X. It's the same thing, okay? D rows, and N rows and D columns. And we want to do a dimensional reduction so that the original maybe D dimension is too high. We want to reduce K. This K is quite similar to our SVD as a K, okay? The first K component. All right. So how can we write the relationship between this matrix, which is n by d, and this reduced matrix, which is y, which is n by k dimension? We can actually write it like this: y equal to xp. It looks pretty simple, right? So y is a reduced dimension, x is a original data table, right? We time a projection matrix P, okay? And I can tell you this P1, P2, Pk, right? So these things are actually these VIs, okay? Because we told you this is equivalent, okay? But we will see why they are equivalent later. Right. So how can you see this thing, this equation makes sense? So how do you know this equation makes sense? Let me change your color. This color is a little bit strange. So in order to see that, let's write it out. Okay, so let's write this out. Yeah, it's okay. Let's write this out. Okay. And as we said, projection matrix means these are orthogonal unit vectors. Okay. And if we write it out, we say that this X times this matrix. Right. This is a block matrix. Block matrix notation. Okay. And in this block matrix notation, let me see. I lose control of my mouse. Okay. In this block matrix notation, X times the first column is the first column of Y. Okay. X times the second column is the second column of Y. Okay. So the dimension matches. So you can use the block matrix notation to write this thing as this. Okay, I hope you can see it. And so in order to see the final dimension reduction process, and these are actually along these V1, V2, V3, these directions, we need a second step. Right? So we just look at the individual item. Let's say we look at these two. Okay. These two can be further written like this. So for example, if, let me pick it. Now, what do it mean by V1 is equal to X times P1? Right? So what is X? X is, again, we have n rows. Right? So maybe this is the first row, this is the second row, it's n row. Okay? That's P1. Okay? And we tell you the row is d-dimensional. Okay? And the P is also d-dimensional. Okay? So this gives you a column vector. Right? So this is the inner product between X1, inner product with P1. Okay? This is X2, inner product with P2. Right? With row times column. So this basically tells you something like this. Okay. So if you look at this thing here, we are saying that this thing is equivalent to, so if you look at the first column, so with Y here, okay? This Y1 is essentially saying, hey, this is your inner product between the first row and your projection direction. Okay? The last element is X, the last row, okay? That's N, Xn, times the first dimension. Right. So this is how you can see this. If you put the Y equal to 1, then let me see, J equal to 1. Okay. J. So what does this tell you? This tells you that, you know, this is a projection. This is a unit vector. This is the direction. If you have x point, this is your x point, this is the origin. Okay, so x1. Okay, and this is your p1 direction. You map. Okay, so you map it around this direction because this is a unit vector. It's like a time cosine theta. This is a projection length. Okay. This is the nth point projection. Okay. So these are basically the coordinates. So this y is the coordinates. Okay. After you, the first row is the first column is telling you the first row, the first data point projected along P1. What's the coordinate? Okay. Then the last data point projecting this one. What's the coordinate? It's okay. Any questions? So put simply, the first column are all those rows projection along P1's direction. Okay. The second column is that projection along P2's direction. It's like these are the new dimensions. Okay. And their coordinates are recorded by these ways. Okay. Any questions? Okay, I hope this is okay with you guys. Okay, so this thing actually is relevant to so-called covariance matrix. Okay, so so we will see how this covariance matrix thing comes about. Okay, so basically we are saying that this is your x. I always say a. Okay, actually this is equivalent to if we compute the covariance matrix. Okay, the d by d covariance matrix. Okay. Of course, covariance matrix is not just this thing. Okay, it's a divided by n. Okay, we will see that. Sure. Okay, and then we can do a PCA over there, and we will get to the result. So first, let's look at what is a covariance matrix when you have a data matrix X. Okay, so this is actually generalized, right? So we know what is variance, right? When the value are scalar. Okay, we are generalize a scalar random variable to a vector random variable x1, x2, x3. Right? So this is a vector, although it's kind of like a matrix notation. It's a vector. Okay, so it's k by 1. Okay? So how do we define it? So in the scalar case, right, your variance is defined as your mean values, right? How far you are, and you square them, and it's for all these data points you take the average. Okay, so this is how you define in the scalar case. But in the vector case, these things become vector because this is a k by 1 dimension. K by these things become vector. Okay, vector times the column vector cannot times column vector, right? So this is an rhythm. Okay, so we will transpose this. So this is column vector times a row vector becomes a matrix. Okay, this is a covariance matrix. And it's in the scalar case, you can also write it like this, right? Because this thing is a scalar, then transpose or not, it's the same thing. Okay, so this is really a generalization over this simple scalar. Okay. But let's see what is a covariance matrix, right? Let's make sense of it. Okay. So firstly, you need to know. I think now you should all know this outer product, right? So I'm not sure how many of you know this outer product. It's different from inner product. Okay, right? And so basically, we are saying that if we have inner product, right? So let me write this again. I'm using the wrong tool. So for example, if you think about you have a vector of x equal to x1, x2, okay? And you have a y equal to y1, y2, okay? So what's their inner product? What's the inner product between x and y? Who can tell me? What's the inner product between x and y? By the way, we assume they are column vectors. Okay. So this thing can be also written as x transpose, which means it's the first row x1 to xb times column 1, 1. Okay. So this row times column is equal to what? Is equal to x1 y1 plus x2, y2, all the way to x3. I hope this is fine. Okay. So this is the one value. Okay. So this is inner product. Okay. But what if we have outer product, which means x, y transpose? What will we have? This becomes a column transpose. Okay. Who can tell me? So let me put things here. Okay, so basically, if you think about x times y transpose, okay? So what is x? X is this thing. So it's a x1, blah, 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 x2. Okay. Okay. And what is y transpose? Y is a column vector. Okay. This is transpose. It's a column. Then we transpose back. Then we have 1, y1, y2. I don't know why it's not appearing. Okay. So what will be the result of these two? I think probably I should use them or not. It's too straight. So what's x1 column vector times the y1 transpose? So this is called output. And who can tell me? So let me give you the answer. So it's the result of matrix, right? So the ith column and this row will give you xi, yj. Okay. This is very simple, right? So the ith column is the ij's value is the ith row, which is xi. Okay. That's the jth column, which is yj. Okay. So that's output. I hope everyone knows this. I think I need to change that. So now, if you're okay with this, right? So let's look at here. So this is basically, this is the row times column. Okay. So then this is the ith item. Here is the first item. That's the base item. This is also the first. This is the one. Okay. So this is basically the first row and the case column. Okay. So we can hope you can see. Okay. And because this thing is output, it's a matrix, right? And when you say want to take expectation of a matrix, it's important to say, hey, I will take an expression over every element in the matrix. This is just a definition. What is expectation? Because this is a random variable matrix. If you do that, you put it inside, you can see who gets this. Okay? And this thing is exactly the definition of covariance matrix. Okay? So, for example, here it's exactly the variance. Okay? This is the variance definition here for the first variable. This is for the case variable on the diagram. But the difference is that, instead of times the same twice, if you have two different variables, you have these two terms. Okay? x1 minus the mu 1, xj, x2 minus mu 2, xj minus 1. So this is becomes covariance. This is exactly the definition. Okay? This is like self-covariance. Is this okay? Any questions? I hope it is fine. So next, let's take a look at why we are saying that. Let's just use the notation. This is A. Okay? If this is A, what is this? Assume that data has been centered. So then the mu is there. Okay? This becomes A. That's A transpose. Right? But again, so sorry. This X is not a vector. This is a vector. Yeah, so we'll see the derivation later. Okay, so for the matrix notation. Now let's take a look at some properties when the X is vector. Okay, keep in mind. So here we are copying something from the internet, but they are using crazy notation. This is a vector. So this is a vector. This is a vector. Okay. So one property we can have is this property. Okay. This is equivalent to say, if you remember, in the scalar case, we have a variance of a random variable x is equal to what? Equal to expectation of the random square minus expectation square of the random variable. Okay. If you I know this form. Okay. This is a generalization of this form. Okay. because now these things are matrices. Okay? Because this vector, this is row vector. Okay, how can we see this following the previous definition? The previous definition is exactly this definition. Okay? We are just the one who derived, we are using this definition. Okay? Now let's see how we can derive some properties. Okay, to prove this theorem, it's very simple to follow definition. Okay? This is the definition we just showed you in the previous step. Okay? Now this contains 4 terms. Okay? So you can write it down. So this is this and this transpose. Okay? You just write all the 4 terms out. For example, this term is coming from minus e, this minus e, and the transpose. So you have the transpose. If you follow the definition, you write it into 4 terms. And now the expectation, right? So you can so linearity of expectation is equal to the expectation of all the 4 terms, each of the 4 terms. Okay, but this expectation of something, especially when a random variable is constant. Okay, it's a specific value. So you take out the constant, you just take the expectation on the left side. This is the same, but the expectation you can take out the right side. And this is, anyways, both are constant. Right? So take the expectation again is the same. And what you need to know is these 3 things are the same thing. Okay? It's like a -2 of those plus back 1. It's just equivalent to -1. Okay? And this exactly proves our theorem. Any question here? I hope this is fine. Another interesting and a very intuitive property is that, right? So if you have a random variable, if you add a constant, okay, it's still a random variable. But again, so this constant is a column vector, okay? Because x is a column vector. Don't be confused by the notation. I think the source I take the formula is not very good, not very professional notation. So if you write this out, we follow the definition of variance, right? So the variance is this thing minus the mu of this thing, right? And this thing minus mu of this thing transpose. Okay, just write it out like before. Now, expectation of these 2 terms, right? This is a constant. You can take the expression of the constant, use the linearity of constant, linearity expectation. It's the expression of each term. Okay? Expression A is A itself. Expression X is X. Okay? So you can write this into this and write this into this. Okay? And the interesting thing is that A and minus A cancel. Right? So what it will give you is a 3rd term. Right? So it's these 2 terms cancel. And this is exactly what? This is exactly variance. Okay? So this is how you can prove it. Right? But this is quite intuitive. Right? So basically, if your variance is like that, right? So your point is like this, you add a constant, you have to move it to here. So variance is still this. Okay? They are still scattered like this. Okay? But if you want strictly proof, you can do this. So all these kind of very straightforwardly carried over from our scalar case, right? Do we have any interesting property? Right. So this is our, this is what we will be using. Okay, this is more complicated, right? So what does this say? So if you remember, right, if in a scalar case, if you have variance and random variable with a constant, if you take a variable, it will become square, the variance. Okay? And this is in the scalar case. But now this is B itself, right? Is a matrix, by the way. Okay, so we are talking about, again, I hate this notation, but this is a matrix. Matrix times a column. Okay? This looks like a value times the matrix, but this is actually, B is a matrix, X is a column. Okay? But it's a constant matrix. Okay? But if you take this matrix out, this time we cannot square the matrix. Matrix has nothing concept like straightforwardly square. Right? So what you do is you time the matrix on the left and time the matrix transpose on the right. Okay? This is quite similar to the quadratic form. So whenever you have something in high dimensional that is quadratic, actually you do one thing on the left, one thing on the right, and one of them is transpose. Okay? So this rule always holds. Okay, let's see how we can derive this. Right? So this again follows the definition. this thing's variance is this thing minus the mu, this thing minus the mu transpose. Okay? And after following the definition, this B is even it's a matrix, right? It's a constant matrix. You can take it out of the expectation. Okay? And then after taking it out of the expectation, you can write out things like this. And so this thing is basically B parentheses X. If you take this whole thing, and then you take the transpose, this transpose, right? And then you basically go in this direction. Okay? You go in this direction. You first take this thing's transpose, which is this thing. Okay? And then you take this thing transpose, which is this thing. Right? This is how you see this. Now you kind of already have a shape that you have a B at the front and a B transpose at the end. Right. But these are constant. Okay. When you take expectation, constant can become. But again, because of the matrix, right? If you time on the right, it should be on the right. After taking. If you time on the left, it take still on the left. Okay. And what's this thing in the middle? This thing in the middle is again the variance. Okay, so that's basically complete. This is the following definition of variance. Okay. Any questions? Yeah, it's quite math intensive in this book. Okay, so in this lecture. And so in general, we have this problem, right? So if you add A, it doesn't impact your variance. But if you time a matrix A, then when you take them out, the constant matrix should time on the left and time its transpose. So this conclusion, that's the number. Okay, next let's look at the PCA. Okay, so we discussed that. So covariance matrix can be computed like this. Right? So this is, remember, this is auto product, right? So this means it's a matrix. We have the i's term, j's term, right? So this is this will be xi minus mu I, xj minus mu j. Okay? But remember, we need to take another expectation. This is by dividing by n. Okay? So this is basically the sample converge matrix. It's a definition of it's a definition of this thing, right? But this is actually the mu. Okay, this is the actual mu, and this expectation is the 1 by n. So this is what we are doing to compute the sample converge matrix. This is the ground truth code, but we only see a bunch of samples, so that's all we can do. Okay, it's a sample converge matrix. It's the same thing as before. Auto product, I take an expectation of all the rows, where mu is the expectation of rows. Okay. And this is d by d dimension, okay? Because there's you marginalize all the n dimension. Right? So this is d by d. Now what we want to do is this. Right? So we know that we have a projection matrix P1, P2, P3. Right? So it's a column. Okay. That's just consider one vector P1. It's a star. Okay. Now we want to. Originally we have this point on high dimension space, but we want to project the coordinates. Right? How do we do that? We do the image. Okay. After doing that, right, these become the coordinates on this line, and then we compute the variance on this line after projection. So this is how we compute. This is the regular, variance definition along the projected P1 direction. Okay. And according to our PCA, we want to, after projection here, like we want these to be spread out as much as possible. Variance line, right? Because we want the original space is it's a very far apart. After projection, still far. Okay. If you take this dimension, then it's disaster. Every point is kind of back to the same coordinate. Okay, you lose a lot. So we want to maximize this variance after projection. And you can write this like here, as we said, this thing is basically variance after projection every point x along the dimension. Okay. And the interesting thing is we can use our conclusion here. Right? So let's temporarily assume that we already pick a particular projection value. Okay? Then we need to take out of the variance. Okay? When we take it to the left-hand side, it's like as before. We take it to the right-hand side, it's transpose. But P transpose P. Again, for this thing, we are using this. Okay? We are, here P is a 1 vector. Right? It's fine. Matrix is n by k. Right? So it can be n by 1. K can be equal to special. So this is beautiful. So you take P1 out and it goes this. Actually, you take a P1 transpose out. That's why the transpose. So now we want to maximize variance equal to we want to maximize this. Right? Let's see here. So this is variance, and we want to maximize this. Here we do have a constraint. So the only constraint is that this is a unit vector. This is the direction. Right? So which means it's a vector length equal to 1. Right? So this is the constraint. This thing equal to 1, which means this equal to 1. Okay. And using this is the constraint. This is the type. Right? So using Lagrange, we add a Lagrange variable on top. This is what we just covered in the previous slide. Okay, previous set of slides. Now this constraint optimization becomes a unconstrained maximization. We want to find a P1 direction that maximizes. Right. Now how can we do this? Right. So of course we take a derivative of this and set to 0. And then we set P to 0. Then that's the best step. This is we talked about. Actually, it's a reason very simple because this is a projective function. This is a linear function. Both are convex. This is minus, but this is a linear function. Let me see how to say this. Yeah. So assume this is convex initially. Okay. So then we can just take a set a derivative p1, which is you can change to 0. Okay. We want to find the one that is this actually concave. Okay. And we want to find the max. Right. So now let's take a derivative p1. What is the result of this? Who can tell me? What's the result of this? Right, we are using this conclusion here. Okay. Right. This is this A in the middle. Right. Now it's a C in the middle. Okay. W is P1, which is the variable we are taking. Okay. So this is CW plus C transpose. Right. But we told you that this C is Converge matrix is symmetric. Okay. I, J is variable, J, I is variable. So the entry is the same. Okay. So that basically it can be written as AW plus AW because this covariance matrix is the same. Okay. It's a symmetric. So this side, if you take a derivative P1, this becomes 2CP. Okay. Now let's take a look at this side. Okay. This side you can easily see that it's equivalent to if you have an identity matrix. Right. If you do something like this, then it's a 2 identity matrix. Okay. And this is minus then minus then. Okay. Right. And you want to set this derivative to 0. Or you say it's here. Okay. These two cancel. This two cancel. This gives you this. The identity matrix have to be 1 with the set. Right. This gives you this. Right. So what does this tell you? This tells you that you just need to compute the covariance matrix of data matrix X of A, right? And then you come to Eigen Decomposition. That's the eigenvector P1. Okay, right? This is the eigenvector because of your covariance matrix. Because P1 times the eigen C by the covariance matrix is again this P1 direction. Okay, this lambda 1 is the eigenvector. Okay, so this gives the conclusion that PCA can just compute the covariance matrix or data matrix, and then do the Eigen Decomposition. Okay, and because you want to maximize this, right? You want to maximize the variance. Right? You will take the first eigenvector. Okay, eigenvector. Okay? Because that will maximize the lambda 1, which is your maximize this variance. Okay. All right. So because time is up, I will continue next time, and let me take attendance for the other two students. Kalyani, are you here? Kalyani? Kalyani? What up, Helen?
Present, sir. I'm here.
Okay. Priya Vaya?
Yeah, I'm here.
Okay, so that's all for today. If you have any questions, just let me know. Okay, today it's a little bit difficult so be sure to watch the videos and slides and summarize the stuff with these. Thank you. Any questions?
Yes, I wonder the center of data, is it related to normalization, something like z-scores or min-max normalization?
Oh, okay. So it's like this score, you also divide by the standard deviation. Here we don't divide by the standard deviation, just minus the mean. It's okay?
Oh, okay. So if you do PCA, if you do not do normalization, just do the center part, this will also work, right?
Yeah, this will also work. It's just depending on, usually you also want to, if you want to, you can also do this score, right? So then every dimension becomes equally important. Okay?
So you do
you do definitely need to center data. Okay? Right. So this is what you show here.
Okay, so you center it first and then you do the normalization, right?
Yeah. So yeah, exactly. So you can center it and then you compute you can divide the standard deviation. Okay, if you want.
Okay. Yeah. Thank you.
You're welcome. Other questions? Okay, so it seems that there are no more questions. If you have a question, feel free to send an email. Okay, and tomorrow there's no class. Okay? I don't know why Canvas is sending that. There's no class. Okay. All right. So in that case, I will see you guys next week, and where we will finish this slide and we'll have a written assignment. Okay. Thank you. Have a good evening.
Thank you. Have a good day.
Thank you. Bye.
Thank you.